Okay, in the last lecture of this week's material, we are going to look at the laws of Boolean algebra. So they are named after a mathematician called Boole, who'd noticed that subsets have a kind of algebraic structure to them. So in the sort of number systems that we're used to, you can add two numbers together. So there's some operation that does that. And there's also an operation where you can multiply them. And if you add them first and then multiply that number by something, then you can expand the brackets. And so you can do, so a plus b all times c is the same as a times c plus b times c. And two of the operations from this actually do behave in this way. So specifically, if you take the symmetric difference as you're adding, and you take the intersection as you're multiplying, then actually you do get an algebraic system in this way. So let's have a look at them. You're going to see these in a couple of different forms. It is equivalent to some laws of propositional logic that we'll come to, and they will be attached to your exam paper so that you can use them for reference. But this is what they look like in set form. So they are just a bunch of relations between these operations that you get. So if you, let's just go from the top. If you take A intersect B, so you're looking for all the things that are in A and in B, well, you may as well be looking for all the things that are in B and in A. So it doesn't matter if you intersect them one way around or the other, you get the same thing. And this corresponds in this algebraic system to the fact that A times B is equal to B times A. Now, unions also have that property. It doesn't matter if you take them either way round. We can see that from a Venn diagram, but it's kind of obvious. We'll look at some of the other one of the more interesting examples in a little bit with Venn diagrams. There is also a fact about multiplication. If you take three numbers and you do A times B and you work out that and you times it by C, then you'll get the same thing as if you do B times C, work out what that is, and then times it by A. And that's called associativity, and it's reflected in the stuff in 3. So in that line 3, these are the associative laws. So they more or less, but so between 1 and 3, these laws tell you it really doesn't matter which order you do your unions and intersections. It does start to matter when you mix the two of them, as we'll see, but let's move on to 4, and I think I will show this one with a Venn diagram because it's worth remembering. But yeah, this is the thing that made Boole be interested. If you take the union of B and C and then you intersect it with A, then what you'll get is the what looks like expanding brackets, so that you can intersect A and B and then take the union of A and C. So let's just have a look at that on paper. So laws of Boolean logic, Boolean algebra. I am going to refer you back to that sheet. I'm not going to write them all out here, but we are going to just look at one in detail. So let's look at the distributivity property. Okay, so for that, the actual, so we're going to have, just set it up formally. So we've got three sets, A, B, and C. They're all going to be subsets of our universal set U. And let's draw their Venn diagram. So the nice thing about having three sets is that you can draw them all as circles. As soon as you get to 4, you have to start doing, you have to start making silly shapes to get all the possible inclusions. But for 3, we can rather nicely just draw them like that. And so this will be my A, my B, and my C. So there are kind of, in fact, 8 interesting places in this picture. I can have elements that are in nothing at all, so not in A or B or C. I can have elements that are in C, but not in A or B, so just this bit here. I could have elements that are in A and B, so that would be this normal intersection here. I could have all the elements that are in A and B and C. This would be this little intersection here. If you add those up, you can see you get 8 different areas of this shape. So what we want to do with distributivity is to see how some of these areas can interact with each other. So the distributivity property it says, I mean, there are various versions of this, but if I do A intersect B union C, then what I should get is equal to A intersect B, so I'm just expanding these brackets, union A intersect C. So let's look at the Venn diagram and see what bits we're going to be interested in. So if I'm doing this intersection, I want all the stuff that's in A, and I want it to be also in B or C. So anything that's in B or C is good, but it also has to be in A. So if I look at all the stuff that's in B or C and also in A, then I get all of this. Right? So everything here is in A, which is good, and it's also in B or it's in C. But any other part of these, of the picture, it's not going to work. So that's the left-hand side. But let's see what we get on the right-hand side. So here I want to say all the stuff that's in A and B. So that would be all of this stuff. Yeah. Together with anything I can find from the stuff that's in A and C. And the stuff that's in A and C is this bit. So let's just try doing that. So I've got that's A and C. And this bit is A and B. And then if I union them together, I get exactly the same shape. So that is showing you why distributivity holds using a Venn diagram. Now there are more formal ways to do that, but that is all you need for this course to be able to describe those interactions. But using these, you can actually prove some of the properties of subsets, and that is one of the skills that you should be picking up. So I will just take an example. So let's look at So what is A, or no, let's say, show that A intersect B intersect C. So if I take this and then I take the complement, that is going to be the same thing as A as the complement of A union the complement of B union the complement of C. Okay, so one thing we want to do if we're going to make progress with this is to remember that this intersection only really makes sense because it doesn't matter what order I do things in. So, but to apply the laws of Boolean logic, I'm going to write the left-hand side in the following way, just as so. And this is just because of, so by associativity. Okay, so let's now look back at the Boolean laws we've got. So we've got two sets here being intersected, and then we're taking a complement. So if we go back to the Boolean laws, and we look for the first time we get something about a complement, so we've got this nice property here that if you take the complement twice, you get back to yourself, and then some other properties about the complement, but we want one that involves two different sets. And so we're going to be interested in De Morgan's laws. And because we are looking at an intersection of two sets and then taking a complement, that's what we've got here. We're going to want to use this De Morgan's law, this first line of number 8. So it tells us if you want to do this complement and you've got an intersection, just take the complements of each of them and then union them up. So let's see what happens there. So this is going to be equal to the complement of A. So I've got two sets here. I treat this as one set, and I've got this one. So the complement of A union the complement of B and C. So by, let's just call it De Morgan. Okay. Now we need to do some more work because this is still not quite looking like the right-hand side. But we can work on this bit here. We've got another intersection with a complement, and we know how to treat those. We just take the complement of each and then union them. So that gives me A complement, union B complement, union C complement, again by De Morgan. And then finally, this is equal to the union of all of them without caring about the brackets because of associativity. So A dash union B dashed union C dashed, again by associativity. So you can do lots of examples of this, just using the laws that we've got in this list here, and you just want to find one of them that is going to allow you to formally change one of the sides that you're looking at to make it a little bit more like the other side. And between that, you can, between all these laws, you can prove quite a few facts about subsets. So that concludes the week 2 material.